All right, section 1.2, Foundations of Math 20, is titled Exploring the Validity of Conjectures. So if you have a ruler, that's great. You don't necessarily need one, but if you have some kind of ruler, in order to explore this math, a ruler might be handy. But anyways, you'll get the basic point. We are probably going to combine 1.2 and 1.3 today, just because 1.2 is super short, and it's just kind of trying to drive home one little point here. So we're probably going to do a 1.2, 1.3 combined lesson. Okay, so let's just review from yesterday. A conjecture is kind of like an educated guess, right? It's like based on observation, you're making a statement about the patterns that you're seeing and what you can use to predict. So that's a conjecture. The type of reasoning, what was the type of reasoning that this involved? Inductive. Very good. So inductive examples up to a general conclusion stated as a conjecture. So 1.2 is exploring the validity of conjectures. And here in the textbook, you'll see that your brain can be deceived. So you've all seen sort of optical illusions or these kind of puzzles where it's like you look at something and you think one thing, but then upon further exploration or verification, you find that, hey, it's not exactly what I thought. So for example, okay, let's take a look at this first optical illusion here. Now, it says make a conjecture about the diagonal AB and the diagonal BC. So here is AB right here, and here is BC right here. So if you look at that diagram, initially, what does it look like? What does it look like? Anybody want to give a guess here? What can you say about those two diagonals? Initially, what does it look like? Sorry? Sorry, I just didn't hear you. Yeah.
Initially, BC looks smaller than AB.
Okay. Initially, I would agree with you. Did anyone else see that? That BC kind of looks smaller than AB? That's the way it looks to me. With a ruler in your textbook, if you have a ruler right now, or even if you just have your pencil, why don't you just take a measurement of AB in your textbook there and see kind of where it ends up, and take a look at BC and try and confirm that it's smaller. Okay, so if you took a little measurement of AB and BC, initially it looks like the AB is bigger, but if we actually take a measurement, you guys all found that they are what? They're the same. Okay, they're the same. Well, that's correct. Take your ruler on there, you can see that they're the exact same length. What about the second one? Make a conjecture about the circles in the center. This one's really tricky too, because if you look at this part right here, this half, it looks like we've got a small circle in the middle and 4 big circles, right? And then over here we've got 1 big circle in the middle and 4 smaller ones. It appears, because of what's around it, tell me if I'm wrong, but doesn't it appear that this middle circle is much smaller than this one, or maybe a little smaller? All right? But again, if you take your ruler and you measure, you would find that these circles are actually the exact same. All right, so here, this one's pretty trippy too. I don't know how they do this happens, but this is pretty crazy. This right here, it definitely appears that these lines are what? These vertical lines are, it looks like they're curved, right? They look like there's some kind of like opening in the middle here. It definitely looks like this area, I would say anyways, that this area in the middle here is definitely different than the area kind of up the middle there. And I think my mouse is broken or something. But anyways, whoa. Why are we going back there? I don't know. Back to the very beginning. So yeah, and if you guys can do this with your textbook. If you kind of tilt your textbook and just kind of look like this angle, like a really sharp, a small angle on your textbook, you can see that those lines are actually what? They are actually parallel, which really is crazy to me. Does it hurt your brain? I'm really sorry if that hurts your brain. But yeah, if you get a ruler on there, and you can even slap the ruler right down there, and you can see that they're actually parallel. It's just the light and dark areas, how they're placed on there, that messes with your brain. That's something else, eh? Okay, the final one, didn't copy it here, but it says make a conjecture about the number of triangles. Okay, the number of triangles here. How many triangles can you find in this diagram?
0.
Okay. I heard some numbers, 5, 7. Then I heard a couple other things saying, well, there's not really one full one on there. And then I heard 0. Okay? So initially I heard some numbers of triangles, and I don't know how many of you, kind of did this and say, okay, well, I see sort of like one here, one here, one here, little one here, little one here, little one here, and then, oh, don't forget this big one here that's cut out. Okay? Look at that, Star of David there, yeah, or something like that. But anyways, if you did that, you're not alone. You're not alone. That's what one would do. But is there another one? Did I miss another one there? The big one, this big one? Did I do that big one? I maybe didn't do this big one. Okay. Anyways, so you might say, there's a number of triangles. But in reality, over here, there isn't really a full triangle. A triangle is a three-sided, closed figure. So we have what looks to be little triangles all over the place, or big triangles, but really there's zero. I think that I would agree with that. So again, some things are trickier than others. It plays with your mind a little bit, what you see or what you interpret, or what's the definition of this, not. So exploring the validity. All right. Let's take a look at, let's see. Where did that go? Nope, not there. There we go. Okay. So, in summary, some conjectures initially seem to be valid but are shown not to be valid after more evidence is gathered. The best we can say about a conjecture reached through inductive reasoning is that there is evidence either to support it or to deny it. So again, we're not talking about proofs here yet. We're not proving a statement. What we're doing is we're making a conjecture, and it can be validated or strengthened by more examples that kind of align with that conjecture, or it can be rejected because of further evidence. Okay, so that's just what it says here. A conjecture may be revised based on new evidence. So here's one more that we can kind of do together here with the visual part. Make a conjecture about the dimensions of the two tabletops. Okay, these appear to be very different. Are there any parts of them that are the same though? And with a ruler or with your little measuring stick, whatever you have there, is there anything that appears not to be true but actually is true? Or what can you guess about this? They're the same, sorry? They're the same height. Oh, okay. So you're not talking about the surface here of the tabletops. You're talking about these heights here? Yeah. Oh, okay. So you can check about the dimensions of the two tabletops. Can you determine? Okay, well, it does say dimensions. So if some of you thought, well, that's the length and the width there, that's fine. But the height is certainly a dimension. So yeah. So it appears that, well, which one appears to be taller? It's kind of a tough one, isn't it? I think you're right. These are the exact same length, but maybe this one appears to be taller because of this space. I don't know. Okay. They have the same surface area? Oh, you're just guessing? Okay. So those of you with a ruler, if you have a ruler, can we do some measurements there? Okay, so measure the width here of this tabletop. What's this one? 1 exactly? In your textbook? 1.0? Okay. What about this length here? 2.5. Okay. And what about this one here? That's 2.5. Okay, so those dimensions are the same. They don't look the same. What about this one? What's this one? It is 1.0? Is everyone finding this as well or no? Oh, really? Oh, now we've got some talk. Okay, so upon further inspection, someone else had 1.3 over here? Yeah. Okay, 1.3 and 2.6. Over here? Yeah. On the same one? Okay, and was this right, 2.5 and 1.0 according to your measurements? Like on the other one?
No, it's the same.
And these ones are the same as well?
The tiny thing is the same as that other side. I don't think.
Boy, we have some disagreement here. We need more people with rulers, I guess. Okay, I'm going to measure this for myself. This is 1.2 right here. The other one is 2.5. Okay, so this is correct and this is correct. What about this one over here, guys? What's close over here? Okay, this is 2.5 right here. 2.5 and 1.2. Okay, so they are the exact same measurements. And what about the height? Did you measure the height too? Is that the same? 2.0.
They're the same measurements. It's 5.
Okay, all right. So the area, these are the exact same if you measure them out. That is really weird. See, it means they have the same surface area. Area 1 is equal to area 1. Okay. All right, so what can you guys tell me about question number 2 here? It says look at this pattern and find out if you see a pattern, which it looks like there's a pattern there. Will it continue indefinitely? What are your thoughts? Anybody want to just tell us what you found here? Yep.
Well, so for the like the what is like the number squared.
Yeah.
So in it there's like 4 ones, and
Yeah.
then it goes up 1, 2, 3, 4, and then 3, 2, 1. So if I
Okay.
like for the 5th one, if there's 5 ones,
Yeah.
it would go 1, 2, 3, 4, 5.
Okay, so you're thinking it'd be 1, 2, 3, 4, and then there would be a 5 there, and then back down. Is that what you're saying?
And then 4, 3, 2, 1.
Okay, and does that check out? Did you check that on your calculator? Oh, wonderful. Okay. So did anyone continue that and go on? And was there, does it go on indefinitely? Is there a limit to this pattern? Did anyone find anything like that? So 5. So did someone try, 10 ones? Like 1, 1, 1? I don't know if your calculator will be able to do that. But what is that one? Okay, so 6 ones, does it still work? What about this? What about 10 ones squared? Anybody do that on your calculator? What does your calculator say? Doesn't go that high? Does your calculator give you like an error or something?
No, it just like says times 10. You can't see the rest of the digits following.
Oh, okay. Okay, so it's pretty big, right? So let's try it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squared. Okay, so it's going to give it to you in scientific notation. That's scientific notation. So this means times 10 to the power of 18. So that means this decimal place would move over 18 times. So let's just check the pattern that we can see. 1, 2, 3, 4, 5, 6, 7. Oh, there's no 8 there. Oh, there's a 9. And then there's a 0. And then there's a 1. Oh, my goodness. So it might not actually carry on, hey? Let's see. Let's back that up a bit. Let's go 1, 1, 1, 1. That's 4, 5, 6, 7, 8. What about 8? Let's see what happens there. 1, 2, 3, 4, 5, 6, 7, 8, 7. This is kind of tough, isn't it? Because that could be rounded to 7. It could be a 6 there. 6, 5, right? So that could work. So what you want to do is you want to make a conjecture, saying like, I see a pattern. I've continued this pattern on for 5 ones, for 6 ones, for 7 ones. But there might be an end, and there is an end. Like it doesn't work for 10 ones, does it? So you might find, say, for 9 ones in a row when you square it, the pattern breaks down. And that's what happens. The pattern does break down. It actually goes up to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back down. And that's it. So that's where it stops. Okay? So again, I'll let you finish that off. Find out what number this is, how many ones that is. And maybe you can figure that out just by extending this pattern. But that's sort of the exploration that I'm looking for. Okay? So you find out this right here. What number is that goes to this number? Because that's where the pattern stops. Okay? All right, 1.3. As we combine these two, 1.3 talks about reasoning to find a counterexample to a conjecture. All right, what is a counterexample? You're going to see a counterexample definition in your textbook right here. Okay? So a counterexample is an example that invalidates a conjecture. So just to build on what we were doing in 1.2 here, right? We found a counterexample. The 10 ones didn't work. The 10 1 squared didn't work. So does this continue on forever? No. How do we know that? Well, we found a counterexample. So 1.3 basically explores counterexamples. And the definition, again, you might want to write that down either in your own words or whatever. But a counterexample is an example that invalidates a conjecture. So it basically proves your conjecture wrong. Okay? Think back to that example that I gave you the other day about me witnessing all the girls in the other classroom across the hall, right? So I'm thinking there's a whole bunch of girls in the classroom, that there's some kind of either maybe it's a girls volleyball meeting, maybe it's just a grade 11 girl group meeting or whatever it is over there. I see more girls come in. Okay, they're all from grade 11. They are all volleyball players. I know that. So that strengthens my conjecture. Then I see a group of boys go in there and they seem to take part in the meeting. Well, that's a counterexample for my original conjecture, isn't it? Unless they're managers or something on the girls volleyball team, I don't know. They wouldn't be players. So I might have to adjust. And now that would be a counterexample. So if you witness something or make an observation that totally flies in the face or totally discredits your conjecture, that is a counterexample. So you may have to search for counterexamples. But how many counterexamples would you need to completely destroy your guess or your conjecture? How many would be enough? Well, if I said that it's an all-girls meeting and I see a boy walk in there and take part of the meeting, all I need is one counterexample and then I have to adjust what I'm saying. So you're right. So some of you said one there. Yeah, all you need is one counterexample to invalidate a conjecture. So we might want to make a note there. Okay. Only one counterexample is required to invalidate your conjecture. So just as long as you know that, only one counterexample is required. If there are more, well, you know for sure you're out to lunch there. So let's take a look. Let's just take a look at your assignment here. I'm just going to kind of skip through here. So there's different number patterns and all that sort of stuff. So look at number 1. Let's take a look at number 1 here. Show that each statement is false by finding a counterexample. So this will be part of your assignments. You might want to write this down and jot down some of these answers, but we'll go through some of them together, okay? All right, a number that is not negative is positive. So that's the first statement. A number that is not negative is positive. Can you think of one counterexample to that statement? Yeah, 0, right. I would say that that's a great counterexample. 0 is not positive or negative, so you could have a number that is neither. There would be your counterexample. Okay?
You just write 0?
So, yeah, 0 is the counterexample, yeah. Show that each statement is false by finding counterexample. So 1a, 0 is your counterexample. Okay. All prime numbers are odd. Okay, so that's a blanket statement. That's a conjecture. Most prime numbers are odd, but can you think of an even prime number? See, that's what you're looking for. An even prime number.
2.
Yeah, 2. Right on. So we've got, 0 is our answer for the first one. 2 is our answer for the second one. No, 2 is the counterexample. 2 is prime, but it is odd. So that's a false conjecture there. All basketball players are tall. Well, most basketball players are tall. But can you think of any short basketball players? Dakota. He's pretty tall. Okay, so Isaiah Thomas, someone said, right? There's lots of small guys. Now,
We write their name.
small, well, I mean, yeah, you can write the name, whatever. Someone that you know or, that's not tall. Now, where's the cutoff for tall? That can be debated. Because how tall is Isaiah Thomas? Do you actually know? He's 5'4"? He's not 5'4".
What's the average
Okay, see, I don't know how tall he is, but let's say he's 5'9", okay? If you're talking to a grade 3 kid, that is super tall. That's tall to some of you girls, right? So, where's tall? Anyways, that can be debated, but yeah, that's a counterexample. Sure, Isaiah Thompson. Okay, take a few minutes to finish number 1. Go ahead and talk about it with a neighbor if you're having any trouble. Go ahead and finish number 1. Take a few minutes.
If it's not,
All right. Okay, so sorry, I have been accused of leaving you at the tough one. Sorry. The height of a triangle lies inside the triangle. Okay, if we have a triangle like this, the height of the triangle is right here. Is that inside the triangle? Yeah. Okay. Is there another kind of triangle that you could draw where the height of the triangle is outside the triangle? Ah, an obtuse triangle. That's exactly right. Look at this. If this is your triangle, and it's situated like this, and this is the base right here, then this would be the height. Whoa! I know, isn't math amazing? Right on. Now, it is true, too, that if you just flip this triangle over, no, not this one, but if you flip this one over, the height might be inside, because this triangle flipped over would kind of look like this. And now the height is inside, if this is the base. Whoa, mind blown. Okay. Yes, math is so awesome. Okay, need any help with the other ones? Okay. I'm just going to interrupt you for a second here. There's some students over here that noticed number 7. They asked about number 7. Let me talk to you about number 7. Clara noticed that the digits 4, 5, 6, and 7 could be used to express each value from 1 to 5. So here's expressions using all 4 of those digits, but only those 4 digits. So she conjectured or guessed that every number from 1...
all boys who are in choir.
Okay, so here's the numbers 1 to 5 using those digits only. So will this work for all the numbers 1 to 20? You do not have to come up with your own way of doing 6, 7, 8, 9, 10, all of them. You don't. Because look at 5 plus 1 is 6. So you could do this plus this is 6. You know that 5 plus 2 is 7. 5 plus 3 is 8 and so on. So up to 10 it works. 5 times 2, right? 5 times 3, that's 15. 4 times 3 is 12. So which ones are not covered by what you're given here? And see if there's a counterexample to this. So for example, 13 is prime. So can you use those 4 digits only to make 13? That would be a good place to start. Or 11, right? How could you do 11? I guess 11 would be, I guess you could do 5 plus 1. Does it say you can't do that? I don't know. Go along that thought process though anyways. So see if there's any that can't be used from 1 to 5 to make all those numbers.